Good morning. Today's lesson will focus on chemical reaction types. We will focus on identifying the types of chemical reactions, whether they are synthesis, decomposition, single or double replacement, or combustion reactions, and we will learn how to predict the products of a chemical reaction. The first type of reaction that we're going to look at is a synthesis or a combination reaction. You'll see the term combination in some of your textbooks or online resources, but for the purpose of my class, we are going to be using the term synthesis. A synthesis reaction is one in which two or more elements will combine to form a single compound or product. Typically also you'll find that heat and light are also produced from these reactions. Now, the key for recognizing the fact that you have a synthesis reaction is the fact that it has only one product. None of the other reaction types will have a single product that gets formed. So that's kind of your clue that you have a synthesis reaction. Now you have two general forms. You have A plus B forms a compound AB, or you could have a compound AB plus element C forms a more complex compound, but still notice there's only one product. That would be ABC. It will contain a polyatomic ion in this situation, and if you remember from the vast majority of your polyatomic ions, they all possess oxygen. So in this type of scenario, element C would be O2. So let's now look at a couple of examples here to show you how we can identify the reaction type. So if you notice with my first example, I have Na plus Cl2 forms NaCl. When we balance it, we have two NaS, one Cl2, and two NaCls. So as I'm setting this up, sodium would represent my element A, chlorine would represent my element B, and I'd have a compound that would form, which would be AB. Now I just want to caution you with this. The reason why it is just NaCl is because of the +1 and the -1 charges for those two elements. So the AB in this format has nothing to do with what the actual chemical formulas are based on their charges. So you'll never see like A2B or AB2 involved in these types of situations. So I'm going to write up one more equation here just so you can kind of see how that second equation would work. So if I gave you a compound such as aluminum chloride, AlCl3, and we react that with O2, that will now form a compound, AlClO3, parentheses 3. So if I were going to balance this reaction, I would have to have two aluminum chlorides, and then that would give me 2 for my aluminum chlorides over here, and I would have 9 for my number of oxygens for that balance equation. Now, in terms of looking at the general form, I have a compound, AB. I'm reacting that with element C, which would be the oxygen, and then it's going to form a compound, ABC. So I'd have the aluminum chlorate as that compound. So you can use that as a means to identify the synthesis reactions. Okay, so let's go ahead and balance a few equations here. So our first equation, we have the reaction between sulfur, which is S8 as an allotrope of sulfur, plus O2 forming SO2. So as we go through this, just to verify, I have element A plus element B forms a compound AB. Now notice again, it has subscripts for the oxygen where it doesn't for the AB. That's perfectly okay. That's just telling you the elements that are present. So as I look at this, for my balanced equation, I have 8 sulfurs as a reactant. I have 1 sulfur as a product. So I'm going to multiply that by 8. That now gives me 16 oxygens versus 2 oxygens. So I'd have 8 for my second coefficient as well. As we look at our second example, I have NaCl plus O2 forms NaClO3 as a solid. Again, you have compound AB plus C, and that forms a compound ABC. So still looking at a synthesis reaction. So now I have my Na and my Cl both being 1 on each side, so I need to start with oxygens in this case. I have 3 oxygens as a product, 2 oxygens as a reactant. The lowest common multiple between 2 and 3 is 6, so I'm going to have 2 for my number of sodium chlorates, and I'm going to have 3 for my number of oxygens. And now, because I have 2 NAs and 2 CLs, I'm going to place a 2 out in front here as well. And for our last example, we have iron reacting with sulfur, forming iron 3 sulfide, Fe2S3. So for this one, I have Fe with 2 versus 1 on the reactants. So I'm going to place a 2 as its coefficient. I have 3 sulfurs as a product versus 1 as a reactant. So I'll have 3 for the sulfurs on the reactant side. And we are showing again A plus B forms a compound AB. So there's our synthesis examples. Let's move on to decomposition. So for a decomposition reaction, it is typically the opposite of a synthesis reaction. Instead of having a single product forming, we will have a single reactant that is breaking down. That single reactant can break down into its constituent elements, or it can form a new compound and elements as well. Typically, these are going to be requiring energy for the reaction to begin. So if you remember, that would represent the fact that these would be an endothermic process at the beginning. We have 2 general forms again. We have the AB breaks down into A plus B. Notice again I have only 1 reactant. Or I could have the second form where I would have a compound ABC as that polyatomic ion breaking down into AB plus C, and oxygen would be your element C once again. So as we look at this first example, you can see here for the mercury 2 oxide, I have a compound AB breaking down into element A plus element B. We could look at a second example where if we had something like KBrO4, that could break down as potassium perbromate. That could break down into potassium bromide, KBr, plus O2. As a balance, I would place a 2 out in front here, and I would have my compound, ABC, breaks down into AB plus C. So now let's balance a couple of decomposition reactions. For the first reaction, we have potassium chlorate breaking down into potassium chloride plus oxygen. Just like our last example, I have ABC breaking down into AB plus C. 1 reactant only, decomposition. When I look at my reaction, I have 3 oxygens as a reactant, only 2 as a product. So I'm going to multiply this by 2 and multiply this by 3 to them both equal 6. And then I have 2 potassiums and 2 chlorines on each side. So I'd have the 2 potassiums and 2 chlorides. As we move on to our second example, this one is more of a binary compound, so it's a little bit easier. I have my compound AB. It's just going to break down into its elements, A plus B. So for my balancing of the equation, I have 1 bromine as a reactant, I have 2 as a product, 1 silver and 1 silver, so I need to multiply the silver bromide by 2 to balance out my bromines, and then multiply my silvers by 2 as well to balance out the silvers. As I look at my last reaction, I have a compound again, ABC. Calcium is my A, carbon is my B, and oxygen is my C. It forms a compound AB plus, in this case, that would be AC, and we would have also BC. So this one, just a little bit of a special exception where instead of breaking down into an element, it just breaks down into 2 simpler compounds. But again, I have only 1 reactant to start off with, so I know that's going to be a decomposition reaction. So as I look at my balancing, I have 1 calcium on each side, I have 1 carbon on each side, I have 3 oxygens as the reactants. If I add up my 2 sets of oxygens on the products, I have 3 as well. So this reaction, again, what I was telling you guys to do in the last video is if it is already balanced, you don't have to write 1s in their place, just write already balanced on the side to let me know that you've already figured that out. Single replacement reactions will occur when an element reacts with a compound to form a new compound and a new element. There are two general forms for this reaction to take place. You have compound AB reacting with element C to form a new compound, Cb plus A, or you could have the AB plus C forming AC plus B. The identifying factor for which reaction you are using is whether or not C is a metal or a nonmetal. Please remember for your ionic compounds that we have the metal located first, so that would be my element A, and then the nonmetal is the second element in the compound, so that would be my B. So in these single replacement reactions, the element that is by itself is going to replace the same type of element in the compound. So if C is a metal, then C would replace A in the compound, and that's why we get Cb. Notice that the C comes first because it is the metal, it's the positively charged ion, so it will go first into the compound, and then I would form the new element A, which would be that other metal. In the second scenario, if you notice, C is replacing B because I'm getting a AC, so I know that the second equation, C has to be a metal for this one to replace B, and I'd have a new nonmetal that would get created in the process. Now, most of these reactions will take place, but we always have to check our activity series. It's a little handout that you will get that gives you an order of reactivities. So it will allow you to see whether or not the reaction will take place or if the reaction is just not going to happen. When you look at this, the element on that list, if the element that is by itself is higher on the activity series, then the reaction will take place. So element by itself, so again, thinking about element C, is higher on the activity series than the element in the compound. That it would replace. A reaction will occur. Now, if the element that is already in the compound is higher on the list than the element that's by itself, then no reaction will take place because that activity series is giving us a list of the orders of reactivities for these different metals. You saw this when we were talking about the periodic trends and the families, when we're looking at the reactions of sodium with water and calcium with water. If you remember those explosion reactions that we did in the fume hood, the calcium, it fizzed a little bit. You saw a little bit of hydrogen gas being produced, but there wasn't any flame. You may have seen a spark that got produced, but with the sodium, we saw a bunch of sparks, and then we eventually saw it explode and burst into flames, showing that the sodium was more reactive than the hydrogen that was part of the water. So that's what we're looking for with the activity series. We'll go through more of these things in class so that you can get a little bit more practice with it. Okay, so let's balance a few more examples here for some single replacement reactions. The first example that we have copper plus silver nitrate forms copper 2 nitrate plus silver. So this is the one that you guys see in the demonstration. When we look at this, I have my compound silver nitrate. It's listed second, but just remember in terms of math, you're able to rearrange your variables. So I'm just going to say that this is AB over here for this, and then I'm going to put element C for the copper. So it doesn't matter which one you put in order. 3 plus 2 still is the same as 2 plus 3. Both are going to equal 5. So I have this here. I look at my periodic table. Copper is a metal, so therefore I know it is going to replace the silver from the silver nitrate. So I have, again, Cb plus A. So we call this, when it is the metals that are replacing each other, we call this a cationic single replacement. Because if you remember, cations are those positively charged elements, which are the metals. So we have cationic single replacement here. When I look at the balancing portion, I have 2 nitrates in the products for the copper 2 nitrate versus only 1 for the silver nitrate as a reactant. So I'm going to have my coefficient of 2 to begin with. And because I have 2 silvers, I'm going to now place 2 for the coefficient on the other side. So as I look at my next example, in this case, remember, hydrogen is one of those unique ones. Even though it is a nonmetal technically, please remember that it also has a positive 1 charge. So it still falls under that cationic single replacement. So I would have my element C plus AB, and you can see I get CB plus A as a result. So from a balancing standpoint, I need to have a 3 for the sulfuric acid. I need to have a 2 for the aluminum, because again I have 2 aluminums, I have 3 sulfates, so that now balances, and then I have a total of 6 hydrogens, so I'm going to place a 3 for the coefficient of the H2, and that now gives me a balanced equation. So let's take a quick progress check here. So I want you to take a moment and identify the type of reaction that you see in the following equation. If you notice, I have NH4 parentheses 2, S, ammonium sulfide, reacts to form NH3, which is a common name of ammonia, plus hydrogen, dihydrogen sulfide, monosulfide gas. So as we are looking at this, again, key factors, I have a situation here where, again, not following all the exact rules, but please notice how many reactants do I have. I only have a single reactant, so therefore this should represent a decomposition reaction. So again, I have a compound ABC, and it is going to break down into AB and then, in this case, BC. So it doesn't follow the true general forms, but because of the fact that we have only one reactant, I know it is decomposition. Okay, so I want you guys to take a moment, pause the video, and try to determine the type of reaction for this second reaction. We have 2 fluorines plus 2 waters forms 4 hydrogen fluorides and an oxygen molecule. So as you look through this type of scenario, again, I have an element and a compound that are reacting together to form a new element and a new compound. So hopefully with this, I'm going to treat the F as my C, plus I have AB, and if you notice, it forms AC plus B. So that should fall under the single replacement category. Our next reaction type is a double replacement reaction. You'll also see it termed sometimes as a double displacement, but we're going to use the double replacement reactions. So for a double replacement reaction, you're going to have 2 compounds that will react together to produce 2 new compounds. The initial substances are always going to be aqueous solutions, and when they react together, you have a couple different possibilities for what can form. You could have a precipitate, which, if you remember, is the solid that will get created and will crash out to the bottom of your beaker or test tube. You could have a gas produced, so from our previous lab, again, you would be able to see bubbles forming. And the one that would not be quite as clear, you would have water that could get produced as well. So typically, the water will get produced in an acid-base neutralization reaction. So we're going to spend an entire third video covering just these specific double replacement reactions. So I'm not going to spend a lot of time on it today. We are going to look at the general form here where we have two compounds. Again, AB plus CD forms AD plus CB. So as I look at this, I have a positive and a negative for A and B. I have a positive and negative for C and D. So for this, you're going to have the positive element from the first compound react with the negative element from the second. So I get AD. And then I have the positive from the second combining with the negative from the first. So that will give me CB for that particular reaction. So let's look at a couple of practice problems here. So the first one is showing you an example of your precipitation reactions. Now, this is something that you guys will eventually learn how to predict for your products. You'll be learning about some solubility rules, in which case you'll be able to tell whether the sodium nitrate or the silver chloride in this instance would form your precipitate. These are the only types of reactions where you guys are going to be responsible for writing your states of matter. So when I look at the precipitation reactions there, you can see I have silver nitrate reacting with sodium chloride. So again, I have elements A and B. In this case, we can treat the nitrate as just a single unit since it's found identically on each side. So I have my AB, I have CD for the sodium and chlorine, and now as a result of that, I will form two new compounds, CB in this case, and AD. It is already balanced. I have one ion of each, so it does not require any balancing. When I look at the formation of a gas, there are some specific reactions that can take place that are going to be exceptions where you can have one of the products being unstable and it will decompose, or in this case you could have just one of your regular products that forms becoming a gas. So in this particular instance here, I have a balance of 2 because I have 2 hydrogens as a reactant and only 1 as a product. So I need to place a 2 for the HCl's. That now leaves me with 2 chlorines. So I need to balance out my sodiums, which also have 2 on the product side. So I've now got my balanced equation. You can see again that I have my compound AB. I have C and D with sulfate being the D, and this will form a compound AD plus CB. So the last type again, that special type, which is that neutralization reaction, we have the barium hydroxide combining with nitric acid to form a barium nitrate solution and water. So in this case, the barium hydroxide, any hydroxide that you have, that is your base. You obviously have the nitric acid, so you always have a reaction of an acid plus a base forming a salt, which is just any ionic compound, and water. So if I look here, again, thinking about what I was telling you guys on the initial video, write out your ions. So I have barium with a 2+ charge off your periodic table. I have the OH with a -1. Because I have an acid, I have H+. And I have, for the nitric part, that gives me nitrate, so I have NO3-. So if I look at my chemical formulas to set up my reaction, I have Ba 2+, OH1-, so I'd have BaOH parentheses 2, and that would again be aqueous. I have the nitric acid, 1+, 1-, so I just have HNO3, and that would also be aqueous. It is going to form the salt, barium nitrate, so Ba2+, NO3, 1-, so I'd have Ba parentheses NO3, 2, and then I would have water as my other product. So again, this would be aqueous, and this would be a liquid. So from a balancing standpoint, you'll notice that I have 1 nitrate as a reactant, 2 as a product. So I'd have 2 for that coefficient. That now gives me a total of 4 hydrogens and 2 oxygens versus 2 and 1. So I'd place a 2 here as well. The last type of reaction is what we call a combustion reaction. And in a combustion reaction, you typically have an element or a compound that reacts with oxygen from the air and releases energy. So remember, because it is releasing energy, that would represent an exothermic reaction. Now, typically, we are going to focus on hydrocarbons for our class. So remember, they have a general form of CXHY that will react with oxygen, and the products will be carbon dioxide and water. This will typically form in what we call a complete combustion reaction. And if we have an incomplete combustion, we have a lack of oxygen, and so instead of having CO2 form, you would have carbon monoxide instead. So you have less oxygens involved in those reactions, so you have CO that would form instead of CO2. Now, when we look at any of the others, because combustion is a special form of a synthesis reaction, something like magnesium metal burning in the presence of oxygen to produce magnesium oxide would be classified for us as a synthesis reaction instead of combustion, but technically it is a form of combustion. So I just wanted to point that out. As an example problem here for you, we have hexene combusted to produce water and carbon dioxide gas. So the hexene, if you remember, is C6H12. Since it tells us that it's combusted, that lets us know that we have it reacting with oxygen, and we're going to assume that it is undergoing complete combustion, and I would have CO2 and H2O that would form. So as I look at the balancing, I have 6 carbons versus 1, so I'm going to have a 6 for the coefficient of carbon dioxide. I have 12 hydrogens for the hexene versus 2 for the water, so I'm going to have a 6 for the coefficient of water. My oxygens, I have 12 for the carbon dioxides plus 6 for the waters, so that gives me a total of 18. I have 2 as a reactant, so I'd have 9 for the coefficient of oxygen. Let's now look at an example of incomplete combustion where we have the hydrocarbon reacting with oxygen to produce carbon monoxide and water instead of carbon dioxide. This is again an example of an incomplete combustion. This is why you have the carbon monoxide detectors in your house, because carbon monoxide is a poisonous gas for us. It will eventually lead to death. So we want to make sure that you have proper ventilation in your area with your furnace so that you have plenty of oxygen. They call that combustible air. And so you want to make sure that you have enough oxygen present to completely combust those hydrocarbons and produce carbon dioxide instead of the carbon monoxide. So if you are starting to produce carbon monoxide in your house when you're running your furnace, it's because you don't have proper ventilation around your furnace. So to do this reaction, we're going to have a little bit of a special scenario here. We can have situations where we end up initially with fractional coefficients, but we just multiply by a number to keep the ratio the same, but make everything whole numbers, and you'll see that with this reaction. So I have benzene here, which is C6H6 reacting with O2. It forms CO plus H2O. So I have 6 carbons versus 1, so I'm going to start by placing a 6 for the carbon monoxides, and then I have 6 for my hydrogens versus 2, so I'm going to place a 3 for that coefficient. At this point, nothing seems strange. However, when we do our total count for the oxygen atoms, you'll notice that I have 6 oxygens coming from the carbon monoxides, and I have 3 coming from the waters. So that gives me a total of 9 oxygens. I have 2 on this side, so to make the 9 equal on both sides, I'd have to have a coefficient of 4.5. So I want to keep my ratio the same, so all I'm going to do is multiply everything by 2. So that would give me a final answer of 2C6H6 plus 9O2 forms 12CO plus 6 H2Os. Now that gives me an even number of oxygens on both my reactants and products. Okay, so the last thing that we're going to do for today is learn how to predict the products for our chemical reactions. So when we do this, what we need to use is those general forms as a way to predict what type of reaction we have and then identify the products from that. So as I look at my first example problem, you'll notice I have Cl2 plus Ki. So I have an element reacting with a compound. So again, I'm going to make the chlorine my element C, potassium my element A, and iodine my element B. So for this, I now know that this type of reaction would represent the anionic single replacement, because now chlorine is a nonmetal, so I know that it is going to replace the other nonmetal, iodine, in this compound. So I'd have anionic single replacement. When we do this now, I would have potassium chloride. So I'd have my AC plus iodine as the B. So as I'm going through this, same type of concept, I'm just going to write them out so you guys will see it this time. So again, always a good idea, write out all of your ions so that you know what you're dealing with. I have Cl minus, I have K plus, and I have I minus. So the K plus and the Cl minus, those would come together to form KCl. And then remember, because the iodine ends in INE, it is one of our diatomic elements. So INE or GEN for the endings, those are your diatomic elements. So I would have I2 to finish off this reaction. From a balancing standpoint, 2 iodines versus 1, I'm going to have a 2 here. 2 chlorines versus 1 chlorine, 2 potassiums versus 1 potassium, I'll have a 2 here as well. Now for this next example, again, I just wanted to go through one of these here with you. This is a non-typical type of reaction, so it will not follow all the same basic patterns. So when I look at this here, I have the NH4NO3. It's going to break down into N2O and H2O. So you'll notice here I've got 4 hydrogens versus 2. So I'm going to place a 2 for the coefficient of water. When I look at this, this would represent a decomposition reaction. Now, again, it is a non-traditional form, so I wouldn't make you guys know that. When I look at the next one, I have an element iron plus an element oxygen. So I have element A plus element B. So I know that that will represent a synthesis reaction, which means that I'll have a compound AB that forms. So when I look at my ions, again, Fe, in this case, I know it can have multiple charges. We're going to learn more about this coming up here, but this one is going to form a 3+ charge. You will learn to identify which one it would be, the Fe2+ or the Fe3+, but again, that will be in a subsequent video. And then oxygen is 2-, so since I have Fe3 plus and O2 minus, that would give me Fe2O3 for the chemical formula. So in this case, 2 and 3 for my oxygen atoms. I need to multiply this by 2 and this by 3. That gives me 4 irons. So I'm going to have a 4 for the coefficient here. And then lastly, I have methanol, CH3OH plus O2. So again, in this case, I have a hydrocarbon plus oxygen. So this is going to be a form of a combustion reaction. So I know in this case, I would have CO2 and H2O that would form. I have 1 carbon along with the 2 oxygens, but I'm going to have that same situation here. I have 2 for that coefficient. I have a total of 4 oxygens, so I already have 1 here plus the 2, so that gives me 3. So to make this side 4, I'd have to multiply that by 1.5. So I'm going to multiply everything times 2. So that would give me 2 CH3OH plus 3 O2 forms 2 CO2 and 4 H2Os. Okay, so this is our last set of practice problems here. So I have an element magnesium plus an element nitrogen. So I know this would represent a synthesis reaction. So I know that element A plus element B forms a compound AB. So determine what the formula of that compound will be. Since I have a metal and a nonmetal, I need to look at my ions. So off my periodic table, magnesium is 2 plus. Nitrogen is 3 minus. Again, notice it is a diatomic element, nitrogen, ending in GEN, so I know it's N2. So now when I look at my formula for the compound, 2 plus, 3 minus, the chemical formula would be Mg3N2. And so now to balance it, I just simply need to have a 3 for the coefficient of magnesium. My next example, I have aluminum plus iron 3 nitrate. Again, I have a compound plus an element, so I'm going to have A, B plus C, and in this case, aluminum is a metal, so I know that I have cationic single replacement for this particular example, and I'm going to have a compound that forms, which would be Cb plus A. Since the C is a metal, it replaces the other metal, which would be the iron. So I would have aluminum nitrate, so AlNO3 parentheses 3, and then I would have iron, Fe. In this case, everything's already balanced. Now, once again, this would be a situation where we would use the activity series to determine whether or not the reaction is actually taking place. And finally, our last example, I have two compounds, so that would be compound AB, compound CD. So again, the A and the B come together, the C and the B come together. This is that special case scenario. Remember, your hydroxides represent a base. Your HCl would represent the acid, so I know I have a neutralization reaction here. So I'm just going to write that down. I have a neutralization reaction, and again, if you want to call that a double replacement, that's okay too. So now for the products, remember we form a salt. So for my ions, I have H plus, Cl minus, I have Ca2 plus, and OH minus. So the calcium chloride, I have Ca2 plus, Cl minus, so that would be CaCl2. And then the water, of course, as the other product, H plus OH minus, would give me H2O. From a balancing standpoint, I have two chlorines as the products versus 1 for the reactant. So I'm going to place a 2 for its coefficient for the hydrochloric acid. I have 2 oxygens versus 1, 4 hydrogens versus 2. So I'd have a 2 for the waters. And that will wrap that up. So again, you need to be able to use those general reaction types to identify what the type of reaction is, and then use your rules for what is forming on the product side using the general forms to determine the chemical formulas, still using your ions to figure that out. So that wraps up this video. We will focus on our next video entirely on the double replacement reactions and learning about your total and net ionic equations. So have a good afternoon.